Welcome back to Logic, Language and Information 2, and to this, the second in a series of lessons on mathematics and logic. The task for this lesson is to use predicate logic to deepen our understanding of the real number line and its ordering relation, with the order being what makes a number line a line. A little warning, this lesson is a bit longer than average, so you might want to break the viewing of it into two. The content is tightly connected, so it needs to be kept together. But don't worry, there are multiple exercises to keep you engaged. Now, to begin at the beginning, the real numbers written blackboard bold R, which is, there, is the collection of all numbers that have a finite or infinite decimal expansion. Among those with infinite and non-repeating decimal expansions, the real numbers square root of 2, pi and e, the base of natural logarithms, are the best known. Let's take one step further back to the progression of number systems as you learnt them at school. At first, there was just the natural numbers, the whole numbers starting with 0. So the numbers 0, 1, 2, 3, 4, 5 and so on, increasing by 1 forever towards infinity. The standard symbol for the set of natural numbers is blackboard bold N. As we advanced in arithmetic skills, we came across the idea of negative numbers as well as positive numbers. By the integers, we mean the set of all whole numbers, positive and negative, extending forward toward infinity and backward toward negative infinity. The standard symbol for the integers is blackboard bold Z, from the German word Zahl, to mean number. The next step up was to fractions. The set of rational numbers, written blackboard bold Q, is the set of all numbers, positive and negative, that can be written as a fraction, m over n, where m is an integer and n is a natural number. So this means we fill in lots of the space between successive integers n and n plus 1, but by no means all the space. The set of rational numbers is still countably infinite, which means that it is an infinity the same size or cardinality as the set of natural numbers. Another step up is required when we get to algebra and try to solve an equation like x squared equals 2. We get the square root of 2, which is not a rational number, as was first established by the Pythagorean school of Greek mathematicians about 500 BC. We don't stop at square roots, but also add cube roots, fourth roots, fifth roots, and so on. The real algebraic numbers are the set of all real numbers that are solutions to polynomial equations with integer coefficients. This fills up more of the space between rational numbers, but still not all the space. Indeed, the set of real algebraic numbers is still countably infinite, so no bigger a degree of infinity than the rationals. The last step to building up the real number line is then to fill in all the remaining space to create a continuous line or continuum. It is only at this stage of the build-up that transcendental numbers like pi and the natural logarithm base e are added. At the end of this lesson, we will see how to express the continuum property of the real number line in predicate logic. We can visualise the build-up of the number systems in a Venn diagram, with the natural numbers n the smallest, and then the integers, the rationals, the real algebraic numbers, and then finally the transcendental numbers to fill out the whole number line. The focus of today's lesson is the ordering relation on the real numbers, formalised in predicate logic. In the process, we'll see how we use quantifiers and the order relation predicate to express the difference between digital and analogue, or between discrete and continuous quantities. For the rest of this series of lessons, we will be working in what is known as the standard model of the real numbers. That is, a model of predicate logic that has the set bold R as its domain and an interpretation I that is standard, in the sense that the standard names for the integers denote the numbers we think they name, and the usual decimal representation names for rational and real numbers denote the numbers we think they name, as do special constants like pi, e, square root of 2, and so on. The one-place predicate symbol n will be interpreted by the set of natural numbers, so that the atomic formula Na is true in this standard model if and only if A is a member of the set of natural numbers. The two-place predicate symbol less than is interpreted by the standard strictly smaller than ordering on the real numbers. The basic arithmetic operations of addition, subtraction, multiplication and division will also be used in expressions to define more predicates on the real numbers. Now, of course, to do this formally, we would need to be working in full first-order logic, including function symbols, and we're not. Instead, we will use simple arithmetic expressions to describe relationships between numbers on the understanding that they are interpreted exactly how we expect them to be, with the meaning they have acquired since we first learnt mathematics at school. The standard model of the real numbers is what is used every day by mathematicians, as well as scientists, engineers, economists, and indeed school students. The difference is that most of them don't think of it as a model of predicate logic. Within this standard model of the reals, we can express the usual inductive characterizations of the natural numbers. For all x is a natural number if and only if either x is 0 or x equals y plus 1 for some natural number y. We can then take the next step up and define the integers. For all numbers x is an integer if and only if either x is a natural number or there is some natural number y different from 0 such that x equals negative y, or equivalently, x plus y equals 0. Notice that this one does count as a definition of the one-place predicate z because there is no circularity, with no occurrence of z on both sides of the biconditional connective. We can also formally define the one-place predicate q for the rational numbers. For all numbers x is rational if and only if there is some integer m and some natural number n different from 0, such that x equals m divided by n. Recall that every rational number has either a finite decimal expansion or an infinite repeating decimal expansion. This means that we, in principle, have a name for every rational number in the form of its decimal expansion. As we shall see after we get to sequence convergence, 0.9999 repeating is another name for the number 1. The real algebraic numbers AR can also be defined in predicate logic, although it is a bit fussier. AR is the set of all real numbers x such that are roots of polynomials with integer coefficients. For example, like 2x squared minus 7 plus 3. The predicate we are particularly interested in is the order relation of less than. The order makes the real numbers align because the ordering is linear, which means that for any two real numbers a and b, either the atomic formula a less than b is true, or the atomic formula a is identical to b is true, or else the atomic formula b is less than a is true. For instance, -7 is less than 3, and 64.21 is less than 157.33, and say 0 plus 1 plus 1 is less than 5 minus 2. We can define the strictly greater than relation as the converse. For all x is greater than y if and only if y is less than x. Likewise, the less than or equal to relation, for all x is less than or equal to y if and only if either x is less than y or else x is identical to y. In virtue of the linearity of the underlying order, these additional order predicates are related by negation. X is less than or equal to y if and only if it is not the case that y is greater than x, and x is greater than or equal to y if and only if it is not the case that y is less than x. We can now start building up a list of properties of the order predicates expressed as formulas of predicate logic. Formula Roman 1 expresses the linearity or comparability of the order, while formulas Roman 2 and Roman 3 express the relationships between the less than and less than or equal to relations. Formulas Roman 4 and Roman 5 express the transitivity of the order relations. If x is less than y and y is less than z, then x is less than z. Formula Roman 6 expresses that less than is irreflexive. For all x, it is not the case that x is less than x, while Roman 7 expresses that less than or equal to is reflexive. For all x, x is less than or equal to itself, x. Formula Roman 8 expresses that less than or equal to is anti-symmetric. This says that if x is less than or equal to y and y is less than or equal to x, then in fact x is identical to y. Formula Roman 9 expresses the bi-infinite property of the ordering. For every x, there exists a y such that x is less than y, and there also exists a z such that z is less than x. The for all there exists quantifier combination, together with the transitivity of the orderings, guarantee infinity in both directions. Formula Roman 10 expresses the denseness of the real number line. For all reals x and y, if x is less than y, then there exists a z that lies between x and y in the order. The next formula, Roman 11, makes this denseness a little more concrete. For any x and y with x less than y, we can choose the midpoint, 1/2 x plus y, as the existential witness z that lies between x and y in the ordering. Formula Roman 12 expresses a basic relationship between the order relation and the difference between numbers. For all reals x and y, x is less than y if and only if the difference, y minus x, is positive, greater than 0, and the other, x minus y, is negative or less than 0. Formulas 13 and 14 express that the order relations are preserved by adding the same number to both sides. Since subtracting is adding the negative, this means that order relations are also preserved by subtracting the same number from both sides. The last formula, Roman 15, expresses that order relations are reversed by taking negatives. X is less than y if and only if minus y is less than minus x. Now, the order predicate allows us to differentiate between analog versus digital type sets of numbers. First, remember from the semantics of predicate logic that any one-place predicate is interpreted by a set of objects in the domain, exactly those objects of which the predicate holds true. In our setting, a one-place predicate P will pick out a set of real numbers, I of P. We will also call it the P set. We've already seen this with basic one-place predicate N, denoting the set of natural numbers, and the defined one-place predicates Z and Q, denoted by the sets of integers and rational numbers, respectively. Now, we say a one-place predicate P defines a densely ordered set of numbers if and only if the following formula is true. Formula says, for all reals x and y, if x and y belong to the P set and x is less than y, then there exists a number z belonging to the P set that lies between x and y in the ordering. Analog quantities are densely ordered. In contrast, digital quantities are discretely ordered. A one-place predicate P defines a discretely ordered set if and only if the following formula is true. For all real x and y, if x belongs to the P set and x is not the largest in the P set, because there exists a w in the P set greater than x, then there exists a y in the P set that is greater than x, and there does not exist any number z in the P set that lies between x and y. Let's look at the densely ordered versus discretely ordered distinction some more. The densely ordered formula says, for all numbers x and y, if x is less than y, then there exists a z in P that lies strictly between those two numbers. In contrast, the discretely ordered formula says that for all numbers x in P, if x is not the largest number in P, then there is a y in P that is the next number in P above x, in the sense that there is nothing in P between x and y. Let's see some examples of assessing the order properties of one-place predicates and sets of real numbers. Our first example is the whole set R. We can use the sort of trivial predicate, x is identical to x, because it is satisfied by all the numbers in the domain. We'll also do a second one while we're here within this example and look at the rational numbers as well. For the whole real line, we can go straight to the formulas Roman 10 and Roman 11 expressing denseness to conclude that the set R is densely ordered. The same argument, by taking the midpoint, works for the rational numbers as well. In example 2, consider the predicate P that picks out the integer multiples of 5. Px holds if and only if there is an integer m such that x equals 5 times m. This P set is discretely ordered. For each x in P, if x equals 5m, then the next number in the P set is 5 times m plus 1, and there is no largest number in the P set. For example 3, consider the extreme example of a size 1 set, here consisting of just the number square root of 2. Turns out that any size 1 set will come out as both discretely ordered and densely ordered, but for trivial reasons. In the formula for the densely ordered sets, we can take x to be the square root of 2 and y to be the same square root of 2, as this is the only number in the set, and that makes the antecedent of the conditional false, and so the whole conditional is true. There are no other instances that make the predicate P true, so we end up with the universally quantified densely ordered formula true for trivial reasons. In the formula for the discretely ordered sets, we can take x to be the square root of 2 with the result that the antecedent of the conditional is false because the square root of 2 is the largest number in the P set, and so the whole conditional comes out true. There are no other instances that make the predicate P true, so we end up with this universally quantified, discretely ordered formula true. For example 4, consider the interval of all real numbers up to and including the number 2 and down to but not including -3. Now, real intervals like this one are always densely ordered, because we can always take the midpoint of 1/2 x plus y of any two numbers x and y in the interval, and this midpoint will always lie inside the interval between x and y. Before we get to an exercise for you, one more example to illustrate another extreme. This one is the union of a real interval and a size 1 set disjoint from the interval. On its own, the real interval is densely ordered, and on its own, as we've seen already, a size 1 set is both densely ordered and discretely ordered. But what happens when we put them together using the disjunction in the defining predicate? In this case, the P set is neither densely ordered nor discretely ordered. We can take x as 2 and y as 5 to give a false instance of the densely ordered formula because there is nothing in the P set between 2 and 5. Whilst if we take x is 0, this gives a false instance of the discretely ordered formula because there is some number in P above 0, but there is no next largest number in P above 0 because it is part of the densely ordered part of the interval from -3 to 2. Okay, so after all those examples illustrating the different possibilities, here are some exercises for you. First, consider the P set whose one-place predicate P is such that Px holds if and only if x squared is greater than or equal to 16. Taking square roots, we get that x is less than or equal to minus 4 or x is greater than or equal to 4. So the P set is the union of two infinite intervals with a gap in between. Now, determine whether A, the P set is densely ordered, B, the P set is discretely ordered, C, the P set is both densely ordered and discretely ordered, or D, the P set is neither densely ordered nor discretely ordered. You have a go. You do a second exercise before I come back to discuss the answers. For your second exercise, consider the P set whose one-place predicate P is such that Px holds if and only if there exists a natural number n such that n is greater than 0 and x is equal to 1 plus 1 on n. So we can list the numbers in the P set in decreasing order. 2, 1 and a half, 1 and a third, 1 and 1 on 4, 1 and 1 on 5, and so on. The numbers get closer and closer to 1 without ever getting there. We'll see progressions like this when we get to convergence of sequences. Now, again, determine whether A, P set is densely ordered, B, discretely ordered, C, both, or D, neither. You have a go. Okay, to discuss the solutions. For exercise 1, the answer is D. The P set is neither densely ordered nor discretely ordered. For failure of denseness, we can take the instance where x equals minus 4 and y equals 4 because there is no number in between them in the P set. For failure of discreteness, we can take x is 4 because there is no number in the P set that is the next largest after 4 because P4 marks the start of a dense subinterval. If you have any comments or questions, look first at the course notes and then go to the discussion board and I'll follow up there. For exercise 2, the answer is B. The P set is discretely ordered. Even though, somewhat counterintuitively, the numbers in this set are getting closer and closer together and closer to 1. This is because for each number x equal to 1 plus 1 on n in the P set, the next largest number in that set is y equal to 1 plus 1 on n minus 1. Denseness in the ordering does not fully capture what is usually meant by analogue or continuous quantities. The continuity or no gaps property of the real line is expressed by what's called the continuum property, or also the least upper bound property of the real number line. It says every non-empty set of real numbers that has an upper bound must have a least upper bound. This least upper bound of a set is unique and it's also called the supremum of the set. For any one-place predicate P defining a set, I of P of real numbers, the continuum property is expressed by the following formula labelled LUBP being true in the standard model of the real numbers. LUBP is a conditional saying. If P is non-empty, because there exists x, Px is true, and P has an upper bound, which means there exists a y such that x is less than or equal to y for all numbers x in P, then there exists a number z that is the least upper bound of the P set. This means z is an upper bound for the P set, and in addition, z is less than or equal to w for every number w that is an upper bound of the p set. If you were wondering about the dual concept of the greatest lower bound of a non-empty set with a lower bound, hang on. It is a consequence of LUBP, which you can get to by taking the negative of all the numbers. We'll see it in the online quizzes later on. Let's look at some examples exploring the consequences of this formula LUBP. We break the analysis into 3 sub-questions. A, is the p set non-empty? B, does the p set have an upper bound? And C, if the answer to A and B is yes, then determine the least upper bound of this set. So, consider the p set such that px holds if and only if x is greater than or equal to pi on 2 and x is less than 2 pi. So the p set is the interval from and including pi on 2 up to but not including 2 pi. For this example, A, p set is definitely non-empty, and B, it does have an upper bound, since it is in fact bounded by, say, take the integer 7. 7 is greater than 2 pi. Then C, the LUB of the p set must be exactly 2 pi. In this case, the least upper bound does not actually belong to the set. Rather, it is the first number bigger than all the numbers in the set. Another example, p set such that px holds if and only if x is greater than 1. So the p set is the infinite interval from but not including 1 up toward infinity. For this example, the p set is non-empty, but B, it does not have an upper bound because it increases without bound. So there is no least upper bound for this one. Now it's your turn. Consider the one-place predicate P such that Px holds if and only if there exists a natural number n such that n is greater than 0 and x equals 1 minus 1 on n, which, with a bit of algebra, is equal to n minus 1 on n. So we can list the numbers in the p set in increasing order, starting 0, 1/2, 2/3, 3/4, 4 on 5, 5 on 6, and so on. This is the sort of progression that we will see more of when we get to sequence convergence. Note also that this p set is discretely ordered rather than densely ordered, as one might expect. To answer, again, work through the 3 sub-questions. Off you go. Okay, so how did you go? The p set here is clearly non-empty, and this one is bounded up above, for example, by the integer 1. From the given options, the only possibility is choice B, that the least upper bound is 1. As usual, if you have any comments or questions, look first in the course notes and then go to the discussion boards and I'll follow up. This brings us to the end of this rather long lesson on the real number line and its ordering relation. In the next, much shorter lesson, we will look at predicates expressing distance relationships between real numbers, so we can express the idea of getting closer and closer to a target number. We'll see you then.